Hello friends, today I will talk about fundamentals of lasers. This will be the first lecture of lasers. So this is the part 1 and in the part 2 we will discuss some other things about lasers. So first of all let us understand what is laser. So laser is basically a device that produces a highly coherent, highly directional monochromatic light, and laser is actually an acronym for light amplification by stimulated emission of radiation. It was first invented in the year 1960 by the person known as Theodore Maiman. Now this laser light has quite different properties from that of ordinary light. So what are the differences between laser light and ordinary light? Here this laser light is actually a coordinated emission, and it is due to the stimulated emission from the atoms, and because of that coordinated stimulated emission the emitted light has a fixed phase and it is emitted in single direction, and also it has a single frequency. So there is no frequency spread in this case, so delta nu is 0. And but the ordinary light is emitted by many atoms independently of each other. So because of their independence the emitted light has random phase and it is emitted in random directions, and also has a broad spectrum, that is delta nu or delta lambda is significant or finite in the case of ordinary light. Here I have listed the 4 essential requirements for the emission of laser light. So the first requirement is the presence of an active or gain medium, which is actually a gaseous material or a crystal or some dye, or it may also be a semiconductor like gallium arsenide. So that this active medium is very important component for laser emission. The second important requirement is the existence of condition of population inversion, in which the higher energy level has more number of atoms than the lower energy level, and to establish this population inversion condition we need some kind of pumping mechanism through which atoms are pumped from lower energy level to the higher energy level. So this pumping mechanism must be there. And finally the fourth requirement is the presence of a resonant cavity which provides optical feedback for this laser emission to take place. Now this population inversion, actually the condition in which higher energy level has more number of atoms than the lower energy level, leads to the condition of stimulated emission to dominate over the condition of stimulated absorption. Only then the laser emission can take place. So if stimulated emission is lower than the stimulated absorption, then there will be no laser emission. Then positive feedback is basically provided by the cavity, and in the cavity emitted photons pass between two mirrors several times, and because of that there exists a buildup of photons, so that we can get laser emission from the device. And finally this laser light, which is actually emitted from here, has some distinctive properties of being highly directional, being nearly monochromatic and coherent, and as well as having very high intensity. So here I have listed some of the important properties of the laser light and also compared it compared it with the ordinary light also. So coherence is actually high degree of coherence is shown by this laser light, both for the temporal as well as spatial coherence. Temporal coherence means the light is coherent for a long period of time, and spatial coherence means the light maintains coherence for a longer length. The coherence length LC is related to the coherence time tau c. With this relation LC equal to C tau c, coherence length can be of the order of centimeters, whereas coherence time is of the order of nanoseconds, and sometimes it can also reach up to the levels of microseconds. Ordinary light is generally incoherent, and there is no coherence between the different waves of ordinary light. Now the meaning of coherence is actually the existence of fixed phase relationship between different waves of the beam, and the phase actually can be predicted from for the laser light. This monochromaticity means the laser light actually is of single wavelength or single frequency, or you can say delta nu or delta lambda is very small. So laser light shows a narrow spectral width, whereas for ordinary light the spectral width is quite large. It shows a broad spectrum. Delta nu or delta lambda is significant. This monochromaticity actually means that all the photons have nearly the same frequency or same wavelength. Laser light is highly directional, so as it moves forward in the medium, there is very less divergence. So the angle of divergence is very small for laser light, whereas for ordinary light the angle of divergence is quite high. So laser beam is a very fine beam, whereas ordinary light spreads in different directions as it moves forward. Intensity of laser light is quite high, and this intensity is given by power upon the area. So this large power can be focused over a small area, so laser light has high intensity. Now the power of lasers, output power of lasers can be from milliwatt to several kilowatts. The lasers used in barcode readers in supermarkets have powers of the order of milliwatts, whereas the industrial application lasers used for cutting or welding etc. of materials may be of having power greater than 20 kilowatt or even more than that. The power of ordinary light is the intensity of ordinary light is quite small compared to this laser light, as ordinary light cannot be focused to a very small area. So large power is concentrated in a small area. That means the laser light has high intensity. Similar, also the other two properties of polarization and phase relation are also shown by the laser light. Polarization means the electric vector of the laser light is directed in a particular direction. Now here three kinds of interactions between light and matter are shown here. So the three kinds of interaction are basically the stimulated absorption, spontaneous emission, and stimulated emission. Now in the first case of interaction between light and matter, that is the stimulated absorption, some atom is in the lower state E1 absorbs some photon of energy h nu equal to E2 minus E1 and goes to the higher energy level E2. So this is the absorption of photon by the atom to go to the upper level or the higher energy level. So this is stimulated absorption. Now in the second case of spontaneous emission, the atom is already in the higher state, and since this higher or excited state has lifetime of 10 raised to the power minus 8 seconds, so this atom can only stay in the upper E2 level only for this time, and it has to jump back to the lower state after this time interval. So in this process the atom is losing energy, and that loss of energy is emitted as photon. So now in this case when large number of atoms are here, so all will be going back to the lower state, so photons will be emitted. Now all these photons are actually independently emitted by several atoms, so there will be no constant phase between them, or all will be emitted in different directions, and there will be no fixed phase relationship between these emitted photons. In the third case, which is actually a controlled emission, also known as the stimulated emission, atoms in the upper state absorb photons, and then this emitted photon as well as some new photons, this absorbed photons as well as new photons are emitted here. Now both these photons have the same frequency, same phase, and are emitted in the same direction and with the same state of polarization. So in the case of stimulated emission, the atoms in the higher states, on absorbing photons, release photons which are exactly twin of the absorbed photon. So in this case there is fixed phase relationship between the emitted photons. Now this rate of stimulated emission must be greater than the rate of induced absorption for the laser emission to take place. Here I have shown the population inversion and the 3-level scheme. So at least 3 energy levels are needed for a laser emission to occur. Now this even level, which is also the ground energy level, here is having a very long lifetime. So it is a stable energy level. Atoms are here for a very long time, and these E2 and E3 are excited energy levels of the atoms. Now this E3 excited state has a very short time of the order of 10 raised to the power minus 8 seconds, whereas this excited state that is known as the metastable state is having a relatively longer lifetime of the order of 10 raised to the power minus 3 seconds, which is quite large compared to this the lifetime of this excited state. So if induced absorption atoms are taken to this excited state E3, then they will stay there in the E3 state only for this 10 raised to the power minus 8 seconds, and then spontaneously will decay to this metastable state E2. So during this fast decay, the loss of energy will be converted into different forms. There will be no emission of light, so no photons are emitted in this fast decay. This is non-radiative decay. Now here the lifetime is quite large, so several of the atoms jumping from this state to this metastable state will stay in this metastable state for a longer time. So the population of atoms will be building up over here, and then after a time when large number of atoms have build up in the metastable state, and there might be a condition in which the number of atoms E2 N2 in this state has become greater than the number of atoms in the lower state E1. So that is the state of population inversion, in which N2 is greater than N1. In that case, the atoms in the metastable state, after absorbing photons, will jump back to the lower state E1, and then photons will be emitted in this process. The photon energy will be h nu equal to E2 minus E1. So the frequency of photon nu is dependent upon the energy difference between the metastable state and the lower state. So all the photons will have same frequency, or you can say same wavelength. So this means that they will have the light of single color will be emitted in this laser emission. So population inversion is the condition of N2 greater than N1, that is the higher level having more number of atoms than the lower energy level. Metastable lifetime is actually quite large compared to the lifetime of excited state, but smaller than the lifetime of this ground state or the lower state. Three level pumping path is here. The atom is going from E1 to E3 after absorbing some photon, and then atom is returning back to metastable state through non-radiative transitions. Then the laser transition will take place between the levels E2 and E1. Now only two levels will not be sufficient to create the condition of population inversion, and hence laser transition or laser emission cannot occur only with two energy levels. Here some important coefficients known as Einstein coefficients and their physical significance is discussed. These Einstein coefficients A21, V12 and V21 are actually the rates of spontaneous emission or induced absorption or stimulated emission taking place over here. So from E1 to E2 level, is induced absorption is taking place by the absorption of photon. Atom is going to the upper level. So this B12 represents the rate of induced absorption. This A21 represents the rate of spontaneous emission. So atoms are returning back to the lower state without absorbing any photon. They are spontaneously decaying to the lower state. So that spontaneous emission rate is represented by A21. Now finally this B21 is representing the rate of stimulated emission. So stimulated emission is actually taking place when atoms in the higher state absorb photons and return back to the lower state. And now these Einstein relations, basically the important one is in the case of equal degeneracies for the two levels. B12 is equal to B1. So rate of induced absorption equals the rate of stimulated emission. In this case, this physically signifies that when photons are incident over here, then these photons are equally likely to be absorbed by atoms in the lower state, that is used for the induced absorption, or equally likely to be absorbed by the atoms in the upper state, that is used for the stimulated emission. So for this is very important thing, because if E21 upon B21 is much smaller than 1, then stimulated emission will dominate over the induced absorption, and which can only occur if a state of population inversion has been established there. So for laser emission, we have to consider the fact that A21 over B21 must be much smaller than 1. The condition of population inversion must be established, and here this A21 over B21 is proportional to nu cube. So this nu cube factor tells us that the rate of induced rate of this spontaneous absorption, rate of spontaneous absorption will be higher at higher frequencies. So in that case, the rate of stimulated emission will be greater than rate of spontaneous emission. This will be difficult to establish, to make rate of stimulated emission higher than the rate of spontaneous emission at higher frequencies. And this is the reason why the X-ray lasers are difficult to build, or the higher frequency lasers are difficult to build. So we have seen that in this lecture, the laser light is actually very different from the ordinary light. It has quite important properties of highly directional, highly monochromatic, and being single frequency, and having high coherence, high degree of coherence, temporal as well as spatial coherence. This laser light can be produced only by having at least 3 energy levels. Now in the next lecture we will see that the 4 energy level system will be better than the 3 energy level system for laser emission. So I think this is sufficient for today's lecture, and in the part second we will discuss some continuing concepts to this chapter of lasers. So till then, thank you, bye bye.